Hey AP Chem, we are going to go on to chapter 10. I will also be posting these notes online for you so you don't have to worry about writing them down while I'm talking over them or anything. And the worked examples that you can find in your textbook will also be on our Google Classroom. Chapter 10 is all about gases. And let's see, there we go. Unlike liquids and solids, gases are able to expand to fill their containers. They are highly compressible, which means you can make them a lot smaller. You can compress them. And they have extremely low densities, and a lot of times they're referred to as vapors. That should be pretty standard. You should know that. We've covered that since freshman year, probably before. Their properties, their physical properties are usually easy to understand because they're very similar between gases. So like, for example, all gases can be compressed. However, their chemical properties are going to differ very much depending on which gas we're talking about. So for example, nitrogen and oxygen make up the bulk of our atmosphere, and their chemical properties differ. So like O2 can support human life, whereas N2 cannot, and they behave as one gaseous material because their physical properties are the same. So while one of them can support life and the other one can't, their physical properties are the same, which means that you can kind of treat that mixture almost as if it was one gas. Pressure is the amount of force that's applied to an area. So if you guys took physics, you should know what pressure is. So it's just P equals F over A. When we're talking about gases, we talk about atmospheric pressure because that's the weight of air per unit of like an area. So when you're talking about atmospheric pressure, you're talking about the gravitational force that's exerted by the gases in the atmosphere for a 1 meter by 1 meter area. This here is a link to a Bill Nye episode where he does a demonstration about atmospheric pressure. I recommend you guys click on it and check it out because it is, first of all, Bill Nye, who's amazing, and secondly, helps illustrate that idea. There are different units of pressure, so we can talk about pascals, which is abbreviated as a PA. That 1 pascal will equal 1 Newton per meter squared, so newtons are a unit of force, and then a meter square is that area, so that's where you get that force over area. You can also have pressure measured as bars, so 1 bar is equal to 10 to the 5th pascals, or 100 kilopascals. Pascal was a French scientist who studied pressure in the 1600s, and he worked with a student of Galileo, Torricelli, and so up until like Pascal and Torricelli worked together, a lot of people didn't believe that the atmosphere had weight because if you think about it, if I go out and move around, I don't feel things holding me back. But it was those two together who invented a barometer, which is where that bar comes from, a barometer to measure the pressure of the atmosphere, and they were able to convince everybody that the atmosphere actually does have weight. More units of pressure are millimeters of mercury, so that's the mmHg, or torrs. A torr is named after Torricelli. These units are the difference in height measured in millimeters of 2 columns of mercury. So as like the columns are connected and as like pressure on one side increases, it's going to push one of those mercury down, and that difference is what we're looking for. So the atmosphere, one atmosphere will exert 760 torrs or 760 millimeters of mercury. Manometer is used to measure the difference in pressure between the atmospheric pressure and that of gas inside of a vessel. So if you're looking at this diagram here, we've got the atmosphere exerting a pressure on this U-shaped tube here. So that'll usually force this down, and then that'll exert a pressure over here or vice versa depending on what the pressure inside is compared to the pressure outside. So this gas might exert a pressure this way, pushing this up, and that difference in height is what they're going to be looking for, and that's what the manometer measures. So standard pressure, you should be familiar with when we talk about STP, standard temperature and pressure. That's the normal atmospheric pressure at sea level. So that's 1 atmosphere. It's also 760 torrs or 760 millimeters of mercury. And it's also 101.325 kilopascals. So at this point, I would like you to pause the video and then go over to the worked example and do examples 10.1 and 10.2. I will be posting a video explaining that as well. Alright, so this is going to be talking about Boyle's law. The volume of a fixed quantity or amount of gas at a constant temperature is inversely proportional to pressure. So inversely means that as one goes up, the other goes down. So if we're talking about a constant temperature, if I increase the pressure, the volume will decrease because as one goes up, the other goes down. So inversely proportional. The guy who discovered this, Robert Boyle, was an English chemist, again working in the 1600s, and he first researched or experimented with this relationship in these J-shaped tubes that you can see up here. The tube on the left had gas that was trapped above a column of mercury. Then he would add more mercury, which increased the pressure, and found that the volume of this trapped gas would decrease. So when you doubled the pressure, you ended up having the volume. So you can see here it went from 60 to 30 because our pressure doubled. So P and V, pressure and volume, are inversely proportional. A plot of volume versus pressure will result in a curve because of that inverse relationship. So since P times V will equal a constant, if you manipulate it so that you can isolate the V by dividing by P, so you're dividing each side by P, you'll get volume equals that constant times 1 over P, which will give you a linear relationship right here. So that's straight line. This is a practical application, so every time we breathe, your rib cage actually expands and your diaphragm contracts, so it increases the volume of your lungs, and because that increases, then the pressure inside your lungs will decrease, which forces air in. Okay. So your air is going to be forced in because you've got an area of low pressure inside your lungs. Then your diaphragm will contract, decreasing the volume and increasing the pressure inside of your lungs, forcing that air to come back out. So you can apply this law or calculate this law, Boyle's law, by taking the first volume or initial volume times the initial pressure will equal the final volume times the final pressure. So V1 times P1 will equal V2 times P2. Then we've got Charles' law here. So it was discovered by Charles, which is a French chemist in the 1700s, late 1700s. He discovered that if you have a certain amount of gas, so you're not changing the amount of gas, that's going to be your constant, at a constant pressure, the volume will be directly proportional to its temperature. So this was the starting volume, then if you add heat, it expanded, because that's the direct proportionality there. Increased temperature, increased volume. Then you cool it down, so decreasing temperature, you're going to decrease volume, which gives us this equation here. Volume divided by temperature will equal that constant, and it also results in a linear relationship because it is directly proportional. Avogadro's law is when we start talking about the amount of gas. So the volume of gas at a constant temperature and pressure will be directly proportional to the number of moles. That should seem pretty obvious. Like if I put more air inside of a balloon, it's going to get bigger, right? Because you're putting more moles inside, so the volume therefore has to increase. So even though it's called Avogadro's law, it's really a combination of this guy, Joseph Gay-Lussac, and Amedeo Avogadro's work. So, or Amedeo Avogadro, sorry. So Gay-Lussac was an amateur who, so he wasn't really a scientist, he didn't do that for a profession, but he flew hot air balloons, and he did that to about 23,000 feet in 1804. And he wanted to better control the balloon, so he started to study the gas so that he could get better control of it. And he made a bunch of observations that were then interpreted by Avogadro, which became Avogadro's hypothesis. And so you can calculate that by taking V1 over N1 will equal V2 divided by N2. So at this point, we're going to stop and we're going to do example 10.3, and we'll come back and finish up, well, not finish up, but do another section of this lecture in another video.